This video is the very last part of our stoichiometry unit, and we're going to be looking at how to compute mass percent, and then something that's related to that, and that is how to calculate empirical formulae when given either percentage or grams, and then how to compute a molecular formula when given molar mass and empirical formula. That sounds like a lot, but it's really not bad, so just hang on and we'll get it done. The first thing is computing mass percent is probably pretty straightforward to you. In fact, I bet you can look at this and guess how to set this up. So stop your video, take a moment, and see if you can figure out how to do it. All right, chances are you are right. And what you've got is mass of Cl, right, over total mass. And that's going to be how the formula works. It's going to be in percent. So you're going to take what's going to be a number under 1, right, a decimal number, and you're going to multiply that times 100% to get mass percent. And that's all there is to it. And there's only one or potentially two parts that are the slight bit tricky. And that is, first of all, you've got to remember how to compute the mass of any molecule. But you'll know how to do that really well, right? So you know that you just take carbon, chlorine, and fluorine, and you see what numbers they exist in, right, in this particular compound. And then you just multiply each element by its atomic mass number, right? And chlorine is 35.4, and then fluorine is 19. So, ooh, I didn't leave myself much room, did I? 24, 35.4 times 4 is 141.6. I hope you do a better job than I did here of making room for what you need to figure out. All right, then I just total these guys up, and I come out with 203.6. And I know that 1 mole would be in grams, right? 1 molecule would just be in atomic mass units, right? And we get that strictly from the periodic table. All right, so this is my total mass, so 203.6. If you want to go ahead and put grams here, you could, but there's no need to, because we're going to have the same unit on top, and we're going to cancel them out. Now, here comes the only part that gets a little tricky. I asked for the mass percent of chlorine, and look how chlorine's expressed there, just Cl. But what I'm really asking for is all chlorine atoms that are a part of that compound. So I've got to take my 35.4, and I've got to multiply it by the number of chlorine atoms, right? So there you go. I got that. I know that's 141.6 over 203.6. And I'm going to multiply that times 100% to arrive at my answer. So my answer is going to be 69.55%, and we are done. All right. Now you say, what about significant digits? Don't worry about it. We weren't given any real data here, so however you do it here is fine. All right. And you know you don't need to worry about significant digits on my tests unless I explicitly ask for things in significant digits. All right, so given this method of working, pause the video and see if you can do this one on your own. All right, and I'm just going to show you the answer here. So I computed each of my values for what the mass of this molecule would be, right? And that goes on the total on my bottom, right? Okay, and then I came back and said what was carbon in this. So again, look at this, multiplied it by 6 because there's 6 of them. Each is 12, 72 total. 72 divided by 180 is 0.4. Then I multiply it by 100% to get 40%. And that's all that's involved in that. All right, so let's go on now and look at empirical versus molecular formula. So we've already studied this. So if this has a faint ring of familiarity, that is why. So we know that when we talk about a formula, the way we always do, and we use the word formula sort of generically, don't we? What we're really talking about is the molecular formula. And the molecular formula is going to show exactly the number of each element's atoms that are there in that particular molecule. So it's counting every molecule. When we get up and we get into in-depth organic chemistry, these molecules can be ginormous. So you could have subscripts that are up over 100, and that just is the way it is. So these can be enormous. Empirical formula says if I can factor down a formula into a simpler ratio, then I need to do that to show the empirical formula. So for example, here I've got C6H12O6, that's sugar, right? And this is showing every single atom that is part of this molecule. And therefore this is a molecular formula. I can take that and say, what's the empirical formula? And I can say all these are divisible by 6, and therefore my empirical formula is CH2O. Feels wrong, doesn't it? But that's what an empirical formula is, and I'll show you why we are particularly interested in these in just a second. Now, look at this question here. What's the empirical formula for C5H8? And if you see it, doggone it, I can't factor it down, can I? So in this case, the molecular formula, C5H8, is also serving as the empirical formula because it cannot be factored down. C6H8 certainly could be, but that's not what we were presented. All right, so that is empirical versus molecular formula. So why are we talking about that? Well, hold on to your hats. Here we go. We're going to ask you that if you are given, in essence, a ratio between different elements that are in a compound, that you can figure out the empirical formula. Now, the first question you should ask yourself is, when you see these, 50% of what? 50% of atoms? 50% of mass? What are we talking about here? You need to just implicitly know that we're always talking about mass. All right? So 50% of the mass, or the weight, of this compound is oxygen, 38 is carbon, 12 hydrogen. Now, the next thing that we need to understand is these numbers are operating as a ratio, right? And what I'm asked to provide is empirical formula, which is also a ratio. But an empirical formula doesn't have any reference point of mass in it whatsoever, right? When I say C5H8, there is no idea how much more mass a carbon atom has than a hydrogen atom. So what we've got to do is take this ratio that I'm given and get the mass out of there. Now, how would we do that? Pause the video, think about it to yourself, and see if you can arrive at the answer. All right, so if you came back and said, we're going to divide each by its relative mass, you are correct. So if I'm 50% oxygen and every oxygen molecule has a mass of 16, I'm going to divide by that. Carbon, every carbon molecule has a mass of 12, right? So I'm going to divide by that. Hydrogen 1, I'm going to divide by that. When I do these divisions, what I end up with is generally not quite perfect numbers. Now here I do. I've got a 12, right? That's nice and clean. Here I've got a 33.166, not clean. Here I've got 3.125, right? So when I divide these, I am not getting crisp, clear integers, right? I've got these. So what do we do about that? Well, I say good enough, right? These are close enough to an integer that I'm just going to ignore those. Okay, and then I look and I say, oh my goodness, look at this. I've got 3, 3, 12. So I've got oxygen, right? 3. Carbon is 3. And then my hydrogen is 12. Now, when you look at this ratio, you say, could this serve as an empirical formula? And the answer, pause your video if you need to think about it, is no, it could not, because these are each divisible, aren't they? So I can divide all these by 3, and come up with OCH4. Okay? So generally we're going to express that as CH4O. But you got the right idea, right? That we are always going to simplify down. So, well, let's do this. Let's start off with what are the steps we did. Number one, we divided each percentage by the atomic mass of that particular element. That was step one. Step two was we took a good look at what we came up with for our results, and we said, are these reasonably close to an integer? And we said, yes, indeed they are. Then we said, can these integers be factored down to a simpler ratio? And yes, indeed they could. So those are the steps involved when we have this sort of problem. Now, I want to point out this. These are just ratios, right? That's all they really serve. I could do the same thing to you and use grams and not percent on these. If I were to use grams, I'm in, I still have a ratio between whatever the gram numbers are. I'm still dealing with mass, so I do the exact same process, whether I'm presenting with percentages or grams. It'll work the exact same way. All right, so let's do another problem together, shall we? Why don't you pause the video, see if you can do this on your own. This one actually has another step, so it may get a little confusing at some point. So get to the point where you're stuck and then come back and watch the rest of the video. All right, so what we do here is, you guessed it, we're doing the same thing. We're doing 36.5 for our sodium. We're doing sulfur at 25.4, right? And we're doing oxygen. I'm going to write ox there so it'll be clear it's not a zero, at 38.1. All right, divide each of these by their atomic mass. And when you do that, you don't come out with beautiful numbers, do you? You come out with 1.587, you come up with 0.79, and you come up with 2.38. All right, so this is far weirder, isn't it? So when you run up with numbers that just are not close at all to anything that you can round off to a whole number, what you need to do is divide by the smallest number. Divide all the numbers you're presented with by whatever the smallest number is. All right? And so in essence, you're factoring these numbers down. When you do that, what you end up, and these are not exact, but you will see that they round up pretty much to a 2, 1, and a 3. All right? So now I am at whole numbers, either exactly or close enough for our work today. All right, so now when I do this, I can say my sodium is Na2. Oh, and by the way, is this an empirical formula's worth of numbers? Yes, because we can't factor it anymore, right? So I'm Na2S, I don't need a 1 there, that's evident. And then I am O3, right? And think about this, does this make sense? This looks like a lot like sulfate, but it's got one less oxygen, so this is sulfite, all right? And then I know sulfate has a -2 charge, so sulfite does as well. Sodium has a +2 charge. So I'm doing this just for fun, this is sort of a victory lap. I can only do this sort of thing when I've got an ionic compound, right? But there you can see that, yeah, this worked out. This worked out great. So again, my process was I take each percentage, or grams if I had grams, I divide by the molecular mass of that particular compound, right? And then I come up with number. And if my numbers are weird like this, I find the smallest one, I divide everybody by the smallest one, and I look for whole number ratios. Not going to be exact, but close enough. All right? All right, so that's all you need to know about that. Now, let's think about this. If I give you a molar mass, an empirical formula, can you find out what the molecular formula is? Let's think about what that really means, all right? So a molecular formula we know is just going to be a multiplier of the empirical formula, and I can find out the multiplier if I have the molar mass. So let's look at that. So we know that a molecular formula divided by an empirical formula, right, will give a certain number, a multiplier. So, for example, if I have C6H12O6, right, and let me go back and look at our most recent computation on that. So if I have C6H12, right, I know that that was 180, all right? My empirical formula would have been CH2O, right? Right? Okay. And then that would be 12 plus 2 plus 16. So that would be 30, right? Is that right? Let's see. 12 plus 2 is 14 plus 16 is 30, right? 180 divided by 30 would be 6. And therefore I know that it's actually H12O6. So that does work out just right. So let's do this one and see what we come up with. So I've got a molar mass, okay, and that's what I have here. So I've got my molar mass of 93 grams, right? And then I've got my empirical formula, and the mass of my empirical formula is CH3O. So I've got times 12 times 3 times 16. So 12, 3, and 16. So I come up with here, oh, I hate doing math in my head. I get 31, all right? So I have 31 grams in my empirical formula, 93 grams in my molar mass, and therefore when I divide these out, I get a multiplier of 3. So I can take my CH3O, and I can say that must be C3H9O3, right? Because I am multiplying each of the numbers in my empirical formula by whatever my multiplier was. That looks like a G, doesn't it? Okay. All right. So those are the only concepts that you need to know about for the test. The rest of this, well, I'm going to stop this here, and there is a separate video that goes through the particle computation recap and then does the balancing assignment that you have on the back. All right.